It's not unusual in calculus textbooks to see something, to see problems along the lines of prove that the limit as x approaches, I don't know, let's say as x approaches 1, let me think of an interesting function when x approaches 1. Let's say 3x times x minus 1 over x minus 1. And you might say, hey, Sal, why did you do this x minus 1 in the numerator and denominator? Well, I did that because obviously you can't have a 0 down here. So this function is actually not defined at x is equal to 1, right? If I had just put a 3x, this cancels out for all the other values. So this is essentially the line 3x, except it has a hole at x is equal to 1. And that's why I did it, because I want to take the limit. And it's interesting to take a limit to a point where the function doesn't exist. But the books will say, hey, prove that this limit is equal to, well, it would actually be equal to 3, right? Prove that, and you essentially have to use the epsilon delta definition of a limit. So to prove this, you're essentially proving what this means. And this means, proving this is the same thing as proving, so you could just prove that given, so if you give me some epsilon greater than 0, and remember, that's how close you want f of x to get to the limit. Given some epsilon greater than 0, in order for this to be true, I need to prove that I can give you, that there exists a, I can give a delta greater than 0, where as long as the distance between x and our limit point, x and 1, is less than delta. And remember, we don't want x to ever get right on top of the limit point because the function might not be defined there. So the distance between x and 1 has to be greater than 0, right? That's what this tells us. So I have to prove you give me an epsilon, that I can give you a delta, and as long as x is within delta of 1, and this is all this saying, as long as the distance between x and 1, right? That's when you subtract two things and you take the absolute value. That's just distance. So as long as the distance between x and 1 is less than delta, then the distance between 3x, let me write that up there, the distance between 3x times x minus 1 over x minus 1, that's the function, right? The distance between that and the limit point, and 3, is going to be less than the epsilon. Right? In a lot of calculus textbooks, they'll write it generally. They're like the limit of f of x as x approaches a of equals L, and so this would be A, this would be your f of x, and this would be your L right there. But anyway, when someone says they want you to prove this, they essentially want you to prove this. I'll give you an epsilon. You have to prove that any epsilon that you're given, or that you give me, that let's say I'm the one that has to prove it. Any epsilon you give me, I have to be able to give you a delta where as long as x is within delta of 1, then the function is within epsilon of the limit point. And how do we do that? And I'll just say, a lot of proofs, it's just kind of there's not a systematic way to do proofs, and that's kind of what makes them so interesting on a lot of levels. But these, they kind of tend to be a systematic way. And this, this problem I've given you to some degree is kind of the easy one that they'll give when they ask you to prove these. But they usually involve starting from this point right here and algebraically manipulating it until this expression right here looks something like this expression, and then you'll have this expression is less than epsilon divided by something, or some function of epsilon. It's like, oh well, as long as delta is that, you give me an epsilon, I can just apply that, take epsilon and divide it by 4 or whatever and use that as my delta. Then I've proved the theorem, and so we'll do that here. So let's start with this. Let's start with kind of where we want to get to, and then figure out a delta that's essentially a function of epsilon, so that whenever I'm given an epsilon, I can say, hey, whatever number you give me, I'm going to give you back a number that's that divided by whatever, and then this will all work. So let's do that. So immediately we can simplify this. We can cross these out. And when you cross that out, you still have to say, well, we can't do that as long as x. They can only happen. You can only do this as long as you assume that x does not equal 1, because at x equals 1, this function is undefined, right? And that's okay, because we only care about the intervals as x approaches 1. We only care about the intervals as x approaches 1. We don't care exactly when x is equal to 1. So that's fine. So then this simplifies to, this right there simplifies to the absolute value of 3x minus 3 is less than epsilon. And then we could factor out a 3. So that's, we could say the absolute value of 3 times x minus 1 is less than epsilon. And you might already see we already have an x1 minus 1 there and x minus 1 there. If we can get this 3 over on this side, then we'll be done essentially. So the absolute value of 3 times some other number, it's going to be the same thing as the absolute value of 3 times the absolute value of x minus 1. And if you don't believe me, try it out with a bunch of numbers. This is going to be positive no matter what. This is going to be positive no matter what. It's going to have the same magnitude, right? And of course, that is less than epsilon. And this is what we say. A lot of times a calculus teacher will say, if this is true if and only if this is true. And that's just a fancy way of saying. So sometimes they'll do a two-way arrow. Sometimes they'll write if and only if, kind of an if with two f's. But that just means if that's true, and if this is true, then that's true. And that's generally the case whenever you just do some algebraic manipulation. You can manipulate this back to get that, or that to get that. And then they'll say, well, if this is true if and only if this is true. But this is just algebraic manipulation, right? Because you can go back and forth between these steps. And that's true if and only if that is true. And then the absolute value of 3 is just 3, right? We know that. Let's divide both sides by 3, and you get, well, I can just get rid of the absolute value signs right there, because we know that's 3. If you divide both sides of this equation by 3, you get the absolute value of x minus 1 is less than epsilon over 3. So what have we just done so far? We've just proved that the absolute value, let me write this in another color. We've just proved that the absolute value of essentially, 3x times x minus 1 over x minus 1 minus 3 is less than epsilon if and only if and only if x minus 1 is less than epsilon over 3, right? So it's like this is true as long as the distance between x and 1 is less than epsilon over 3. So we can just use epsilon over 3 as our delta. Remember, the whole point of this was like, you give me an epsilon, you give me a distance, or you say I want to be within this distance of my limit point. I want the function to be that close to the limit point. And this is just the distance between the function and the limit point, right? This is f of x. And this is the limit that it approaches. So you want to be that close. And I say, well, you're going to be that close if and only if x, the distance between x and 1, or the distance between x and the value it's approaching, is less than this. And we just proved this algebraically. So whatever number you give me, if you say, Sal, I want to be within 1 of the limit point. I want f of x to be no further than 1 from the limit point. Then I'll say, okay, then I'll give you 1/3, right? As this is true, let me write that out. So let's say you pick 1 as an epsilon. So you say, hey, you need to prove to me that there's some x value where as long as the x value is no more, there's some value of delta. So as long as we're no more than delta away from 1, then the function itself will be no more than 1 away from the limit value, right? And so I say, well, you gave me an epsilon is equal to 1, so I could just say this is, we just proved if and only if absolute value of x minus 1 is less than whatever number you gave me divided by 3. And that actually makes a lot of sense if you graph this equation. Let me see. Let me draw the x-axis, y-axis. We already established this thing looks just like the equation of 3x, except it has a hole at x is equal to 1. So let me draw the graph. It'll have slope. It'll have a slope of 3, so it'll be pretty steep. It'll look something like that. And when we're at 1, this point right here, there's a hole, right? This is 3. So all we're saying, we just proved that, so if you said that you wanted to be within 1 of our limit point, that's like you giving me an epsilon of 1. So if this distance right here is 1, right, which would be a pretty big number. So you want the function to be within 1 of our limit point, right, because this is the limit point. Then all what we're saying is you just have to take 1/3 of that. So we just have to be within 1/3. So this distance right here is 1/3 away from 1. Or we could have said it more generally. If this is epsilon, this is epsilon. This would be epsilon over 3. This is epsilon over 3. And the reason why this is a proof, because it shows no matter what epsilon you give me, I can always find a delta, because I can just take whatever number you gave me and divide it by 3. And I can divide any real number greater than 0. I can divide any real number by 3. So I can always, no matter what you give me, I can always find you something else. And therefore, I have proven by the epsilon delta definition of limits that the limit as x approaches 1 of this is equal to 3.